Do you see my slide? Okay.
Yeah.
So
Yes.
okay, so today's topic is longitudinal data analysis with clustered data. Well, also some components. Well, I'm going to talk about this random slope, which I talked once some time ago last year. And the schedule is as follows. Today, I'm going to touch, well, first part of longitudinal data analysis. And next time, I'm going to cover another part of longitudinal analysis. And afterwards, maybe I may close this mini start session because I can find out any other topics. Or if you want to present something, you're quite welcome to present, like PCA analysis, which Uriel is familiar with, for example. But as of now, from my side, maybe next time is maybe the last time to make presentation. As of now. So if you have any topics you're interested in, please let me know. And if there are any topics you want to present, please raise your hand as well. And objective of today's session is to review options for exploratory data analysis for longitudinal data analysis with cluster data to select a more appropriate model or models. And well, background, multi-level analysis is a special case of longitudinal analysis. Up to now, we focus on multi-level analysis, but today we are going to talk about this longitudinal data analysis. And multi-level analysis is a special case of longitudinal analysis, actually. And when we follow the same unit, for example, individuals, cities, longitudinally, the data from the same unit are correlated. For example, well, physical and physiological indicators from people like anthropometric measurement, height, weight, BMI, and biochemical data from blood or urine. These are correlated if we get the data from the same person, as you can imagine, and also birth and mortality rates from the same city, they tend to be correlated. And one peculiarity of the longitudinal data is that the correlation of data from the same unit can depend on time. This one, I think you can understand intuitively. So observation with shorter time differences are similar or more correlated, and observation with longer time difference are less similar or less correlated in the same unit. Say we measure blood cholesterol level today, tomorrow, the day after tomorrow for 3 days. I assume that these 3 measures should be very similar. But when we do the same thing 1 year after, this measurement may be, I think, similar to the measurement we measured this year, but less correlated as compared to measurement we do within several days. On the other hand, in multi-level analysis, we assume that observations within the same unit are correlated similarly. For example, in the city, there are many people, and when we use multi-level analysis, we assume that the correlation between person 1, person 2, person 1 to person 5, they are kind of similar. This is what we assume when we do analysis. And in Survival, we use cluster data for cities within countries, or cities nested within countries and people nested within cities. And this time we are going to talk about longitudinal data, which is going to add another layer of clustering. So measurement in year 2000, 2001, 2002, 2003, and so on within the same city. So this is another layer of clustering or nesting structure or nested structure. And well, what to do? And we usually use mixed effects model. And Well, the idea is that after modeling the fixed and random components, residuals, which are differences between fitted and observed value, are assumed uncorrelated. Or sometimes they are still correlated in some setting, and we need to model additionally. Although it's not that very common in, let's say, in a lot of analysis. And in this, here I showed graph to have some image about mixed effect model. And this is a recap of what we talked some time ago last year. So here in the graph, it shows systolic blood pressure on the vertical axis measured over time from now up to 10 years later for person 1 and person 2. And we want to know what is the overall association between blood pressure and ear, but accounting for correlation structure. And we use random intercept and slope model, which is written here on the left-hand side. So with this model, well, we get this overall, how can I say, model for overall mean, which is given by this equation. So systolic blood pressure, or mean systolic blood pressure dot mean overall at time t is given by this equation, beta naught plus beta 1 ear. So this means that so intercept here at time 0 is given by value beta naught, and the slope was say 1 year change from starting from 8th year up to 9th year. So this slope, the blood pressure increased by beta 1. So this is explained by this equation or fixed component of this model. But still, there's a problem here, as you can see. So this is a observed value, and when we take the difference between observed and fitted for person 1, the difference between this and this, they are always positive. And for person 2, the difference is always negative because their values are always, well, the person's 2's values are always lower than overall mean. So they are still correlated. So what do? We also consider this a subject-specific model, which is explained by using fixed component and random effect. So systolic blood pressure of person 1 at time t is given by this intercept beta naught plus b01, and slope is given by beta 1 plus b11. So these b are random intercept. So in other words, well, this person's intercept is given by beta naught plus b01. So here is beta naught, and the difference between this point and this point is given by b01. So it's a subject-specific intercept, which is given by this value, beta naught plus b01. And slope as well. Slope from one unit change by 1 unit increase in ear. This is an increase in person 1, which is given by beta 1, which is the overall slope, plus subject-specific difference, which is b11. Right? So this slope, the slope of person 1 is higher by b11 as compared to overall mean. And similarly for person 2, well, this is the equation, SBP, systolic blood pressure of person 2 at time t is given by this equation. And so his intercept is given by beta naught plus B11. So obviously B11 is going to be negative value. And the slope of this person too, which is shallower as compared to overall, is given by this, and which is equivalent to beta 1, which is the overall slope, plus random component B1, 2. So this is how we model using this mix effect model with random slope and random intercept. By doing this, we assume that now the difference between observed and fitted value, well, where you see these red line and blue line, now they are not correlated. So we can do this analysis. And today we are going to use data from Chile, which is a Chilean death registration between 2005 to 2015, which you can see in our Google Drive. And as usual, these are simulated data, which is different from actual data to maintain data confidentiality. And sample size is 440, sex and age specific cities. So, well, why 440? Because there are 20 cities for 11 years of data and for men and women. This is the reason why we have 440 data. So one row contains a number of deaths in specific city of specific year in male or female. And these are variables included in the data set. So in this example, we have 3 levels with 2 nesting structures. So within country, Chile, we have 20 cities. So they are clustered within the city. And we have data from 2005 up to 2015. So these data also, they are correlated and they are nested within each city. And this is a structure we have. And aim for today is to explore trends in mortality in Chile between 2005 and 2010, separately for men and women, to decide the model we should use. Or in other words, how to accommodate within country clustering and within city clustering. And the first step is to do this, which is famous, well, I should say not famous, but which is called spaghetti plot. I don't know how to say spaghetti plot in Spanish. Tacherin or no?
I don't know that name in Spanish, no.
Okay. Well, it's called spaghetti plot because it's like spaghetti, well, many lines of spaghetti. And so object of this, well, first of all, well, I have to explain what it is. So vertical axis is a mortality rate and horizontal axis is year. And one black line shows the trend of mortality by year. And the red dotted line, these are country average trend. So in both male and female, there is an increased trend in mortality. And also the vertical axis mortality is shown on a log scale, because when we model, we are going to use, well, this is a count data, so we are going to use Poisson model or negative binomial, both of which we connect the equation after we are going to connect the equation using log. And this is a reason why mortality rate is shown on a log scale. And well, for example, for men, the last was this city. So you see that the mortality is kind of increasing over time, roughly. And the top one, the highest one, it seems it sounds increasing. But in the middle, there are many spaghettis or many lines, so it's somehow difficult to judge what are trend in other cities, and when they have many cities or many units. But still, we can get some overall idea of what's happening for the mortality over time. And this is the first shot we may do. And so it was busy, so why don't we separate by city? So for both men here, I will change my pen. So for men and women, stratified by city, 1 means city 1, 2 means city 2. And also I superimpose this blue line. This is a fitted straight line on the observed data. The main purpose is if we can assume that the trends are linear or not linear. And what do you think? Well, by eyeballing these graphs, for me, it seems reasonable to assume a linear trend. I didn't see big departure from linear trend, well, except for some, well, for example, 11, maybe not, but still, it's not that bad to assume the linear trend. Then, so what we're going to so as a whole, as a country, what is a general trend? Let's compare across cities. And as you can see here, we see increasing trend in many cities for both men and women, but some city we see some decline. At the same time, the steepness of slope sounds different. Also, the cross-sectional, or how can I say, the mortality level differs by city as well. So this comparing city 11 and city 12, there is a difference in mortality rate in general. So I superimpose all this linear trend into one graph. And I think the slopes or increasing trend or decreasing trend, the trend are different by city. As I mentioned, sometimes they are increasing, sometimes they are decreasing. Also, the baseline level of mortality there also differs. So this implies that it makes sense to use both random slope and random intercept. Random slope because slopes are different, and random intercept because the initial value of mortality rate is different. So here we try, in this exercise, we are going to try both mixed effects Poisson and negative binomial models. A mixed effects Poisson model is given by this equation. This IT means this was the number of deaths in city I at time 1, which follows Poisson distribution with this parameter lambda IT, which is a expected mean of the number of deaths. And the equation is as follows: log of expected number of deaths at time in city I at time 1 is equal to, well, log of this one equal beta naught I. This is a intercept, but you see I subscript here. So this intercept is city specific plus beta 1I. So you see I subscript here as well. So the slope is also vary across cities. Plus offset term, which is a population of city I at time t. And mixed effect negative binomial, almost the same. Only the difference is we have another parameter here to account for over dispersion. So the interpretation of these beta coefficients, they are the same between Poisson model and negative binomial model. And we use robust variance estimator to account for any misspecification of the variance component, especially for the Poisson model to account for possible over dispersions. Because of Poisson, we assume that mean and variance, they are the same, but sometimes there is over dispersion. And to account for this, we use a robust variance estimator. But we apply this same technique for mixed effect negative binomial model. So this is the result. Only I'm showing the result given for women from Poisson model and negative binomial model. And well, by the way, this t was given by this equation times equal, t was equal to year minus 2005 divided by 10. So when t equals 0, it means that year 2005, and 1 unit change in t means 10 years difference between 0 and 1. So this this value shows expected rate ratio in mortality in 10 years. Okay, so in this case, we will roughly 9% increase in mortality in 10 years in women in general. So look here, IRR is 1.09 from the Poisson model, and from negative binomial, it's the same 1.09 or 1.10. And confidence interval with this one 1.07 up to 1.12, here 1.07 up to 1.12. So they are quite similar in estimation. And also this intercept, which is the value or mortality rate at 2005. This is 4.9 with this confidence interval and 4.9 with this confidence interval. So the estimation for fixed component, they are quite identical between these two models. And how about random component? Well, this is a variance of random slope. The first one is for random slope and the second one for random intercept. Well, okay. But here for mixed effect negative binomial model here, so this implies that, well, it's very small, it's almost 0. So it means that there is no difference in slope across city. This is something I noted from negative binomial model. So we keep this in our mind. And then when finally we want to, when we want to finalize our data analysis, we have to choose which model, which data we are going to show, Poisson or negative binomial. So let's look at the goodness of fit of the model. The blue line shows individual fit, meaning I fit the Poisson model for each city. For city 1, I run Poisson model. For city 2, another Poisson model, and so on. And I got this linear line. This is a kind of observed trend, which is the same as the line we saw previously. And the red line, these are estimates given by mixed effect model. So if blue line and red line, they are very close, it means that goodness of fit is good. And if they are far away, maybe not. But anyway, this is what we get from Poisson model, men and women. And the next one, this is a negative binomial model. This is Poisson, and this is negative binomial. And which is better? Poisson or negative binomial. Poisson negative binomial. Somehow it's difficult to say, I think. They are somehow different, but somehow close. But when we look at closely negative binomial model, the red line, they are kind of parallel. Because if you remember, here, the random slope, we got almost 0 here. So it means that according to this negative binomial model, the slope for each city, they are very close. Whereas with Poisson model, they seem somehow different because it's somehow different from 0. Well, but still, it's somehow difficult to compare which is better or not. So we plot another one, stratified by city. So it's a little bit busy graph. Blue line, green line show individual fit. So again, individual fit means I fit the model for each city. City 1, one model, city 2, another model. And blue line shows estimation from mixed effect Poisson model, and red line shows estimation from mixed effect negative binomial model. And how do you see? For some cities, they're very close. We didn't see any difference between them. But for this city 9 for men, we see difference in estimated line here. City 12, city 17, city 20 a little bit. And for women, some differences was the 11 and so on. And well, so it seems that there is a difference for city estimation between Poisson and negative binomial. And according to my eyes, it seems that this blue line is somehow close to green line as compared to red line. And let's superimpose actual observed trend. And let's see this one, men, city 9. Which do you think better? Red line, blue line? So the green line is a fitted model specifically for city 9. And blue line is somehow, I say, it was decreasing trend, but it's kind of flat, and the red one from the model from negative binomial, it's kind of increasing. So the question is now, which is better? Well, up to now, it seems that Poisson model seems better than negative binomial. But maybe it's possible that, well, these city, where we see the difference between this model, maybe their city size could be smaller as compared to others. Maybe this is the reason why we see different lines. But I haven't checked about the sample size, so this is what we have to do if we see this type of things. And let's look at the coefficient table again. So this is for men and women, comparing estimated coefficients for Poisson, from Poisson model and negative binomial. So time in 10 years. So here, overall trend, time in 10 years. So 0.5, 1.05, 1.06, and very similar, the same confidence interval for men, and very similar in trend, difference by 0.01, so it's almost nothing, and confidence interval is the same. And how about random, not random, and how about the intercept or rate at 2005? So the estimate is the same, and confidence intervals are the same. So if we are interested in only this part, in general, overall, what is the effect in time, and what is the rate at 2005, it doesn't matter which model we take, Poisson or negative binomial. However, say we want to also present this one. There is a difference between Poisson and negative binomial. Let's go to range of intercept. where 95% of city fall in. How do I calculate it? It's given by this equation, exponentiated quantity, this quantity, and this quantity, what is it? Coefficient for intercept plus or minus 1.96 times standard deviation of random intercept. And from this one, I calculated this one. So again, this one, not again, this confidence interval shows accuracy of this estimate. Okay, this confidence interval shows accuracy of estimated mean, estimated overall mean. And this one shows how the rate in 2005 varies across cities. Uriel?
Yeah, just a quick question. You've computed these confidence intervals as the parametric confidence intervals, sort of, because you could also have computed them by hand, right?
But when you say parametric, you're referring to there is a method which can be calculated non-parametrically.
Yeah, I mean, just that you're using the properties of the normal distribution to compute the intervals, but you could also have computed the slope for each city and then did a sort of non-parametric confidence interval, right? I mean, 95% of the values lie between this and that.
Yeah, sure. And this one, well, for clarification, this one is given from the model with normal, well, assuming that the random intercept and random slopes are normally distributed. So this is not from the actual data. Yep. And so when we compare these two range, for random intercept there, well, not random intercept, range of intercepts in which 95% of cities are expected to fall in according to the model. Maybe this is the most appropriate expression I should use, is this one. So there is no difference between Poisson model negative binomial and for women as well. But when we look at this range of slope in which 95% of city falls in, there's a difference between these two. Well, Poisson negative binomial, Poisson and negative binomial. Negative binomial confidence interval is almost nothing, or it's the same as this one, because if you recall the slope, the random slope for negative binomial, it was almost zero. Okay, so if you are interested in showing this part, it may matter if you want to show Poisson negative binomial. But if you are interested in only this component, and the random part is just to account for correlation structure in the model, it may not matter which one you want to use. So it may depend. Okay, so this is a summary. So we look at how we assess time trend with visual aids in order to decide how to use random intercept and slope more appropriately. And also, we also reviewed ways to assess the goodness of fit of the models. And next time, so usually this is not study aim. Study aim is, okay, we have cluster data in terms of the level, like cities within country, people within city. This is a structure. Also within city, I have multiple years of data. So we have cluster data. We cannot apply usual regression model. So we apply this specific model, mixed effect model, to account for it. But now we want to know certain exposure, effect of certain exposure with outcome. This is what we usually want to do. So this is a topic we are going to cover in March. Do you have any question? Nothing. Yeah, Uriel, go ahead.
I actually have a suggestion for a topic.
Yeah, go ahead.
Intervention analysis, such as synthetic controls, differences in differences analysis, placebo tests, and so on.
Okay. Are you familiar with this, Uriel?
Yeah, I'm studying a little bit of this right now for our Sarlball papers.
Okay.
And I think it's very interesting because it lies on the regression framework anyways. So.
Great. So are you willing to present your are you willing to present in April?
I have to check with my PIs.
Yeah, check with PI, and then if she assume if she's fine, well, go ahead and present, and so that the people can learn about this method.
Yeah, perhaps if not in April, later on this semester, but I think this is a really interesting topic.
Okay, and also you're familiar with PCA, I think.
Yeah, a little bit for our paper here. I'm studying it also, but not sure if I could give an entire seminar about this.
So it's up to how you confident you feel, and also depending on what your supervisor say.
Yeah, I'll get back to you.
Yeah. Thank you, Riel. Any comments from other people who participated today? Okay, seems that so if you have any additional questions, that may come up later, please let me know so that I can answer appropriately. Okay.